Hello, in this video I want to talk about something related to polar form, which is the way complex numbers in polar form interact. And it might not seem obvious that these things have much in common. The square root of -1 giving us all these imaginary and complex numbers on one side, and on the other side thinking about things in terms of distance and angle. But it turns out these interact in a way that makes certain calculations much easier and ultimately gives us some very fascinating results. So let's just remind ourselves that a complex number is one we can write like this. We will recall that I is our name for the square root of -1. That's called the imaginary unit. Right? There's no real number with this property, but we invent this imaginary unit, sort of the imaginary version of the number 1. And then we simply combine a number that's a real number with some multiple of that imaginary thing. So an example could be something like 2 minus 1/2 I. It is the real number 2 minus this imaginary number 1/2 I. And just so you know, complex numbers feel very abstract, but they are genuinely useful. There are some calculations where if we open ourselves up to the existence of complex numbers and do the computations in terms of complex numbers, in the end, all of this imaginary stuff cancels away or is irrelevant in one way or another, and we're left with a real solution that makes sense to an actual physical problem. Right? So you can think of complex numbers as a tool for making certain kinds of calculations easier, even though it feels strange sometimes we get the results we want by being open to the concept of complex numbers and imaginary numbers. Now, each complex number has both a real part and an imaginary part, so it's sort of two-dimensional. Right? We need two regular real numbers in order to understand a single complex number. So we can't put them on a one-dimensional number line, but we can put them on something two-dimensional called a complex plane. This is sometimes called an Argand diagram. And the way we do this is if we have a complex number a plus bi, we graph it as though it's the point a comma b. So basically what happens is our regular number line becomes what's called the real axis. So as we move along this number line, we have ordinary real numbers. Here's 0, here's 1, here's 2, here's -1, etc. But then we imagine we have this imaginary axis. And along the imaginary axis, we count using imaginary units. I, 2i, 3i, etc. So if we have a complex number, we can think, well, it has a certain real part and a certain imaginary part, and that's how we plot it. So for example, the number 4 plus I would be 4 units in the real direction, 1 unit in the imaginary direction. The number -1 plus 2i would be here. So it's really just representing these numbers as though they are points because they feel very two-dimensional. And it gives us, on the one hand, just a sense of when complex numbers are close to each other, but we're about to see something even more convenient. It turns out it will be super helpful if we can represent a complex number in polar form. So let's just think about this. Here is some complex number, I'll call it z, which is a plus bi. So it's like the point a comma b, but also we can think here's this distance r, and here's this angle theta. A is basically playing the role of x, b is basically playing the role of y. We know that in terms of our conversions between rectangular coordinates and polar coordinates, x is equal to r cosine theta, y is equal to r sine theta. So we can make some substitutions here. a plus bi. Well, a is the same as r cosine theta, and b is the same as r sine theta. And both of these have an r, so we can factor it out. So this is the same number, but it's the complex number written in a way that emphasizes its polar coordinates. So it's still a complex number. We can still see that I in there. And we would always have this pattern where we factor out the r and then it's cosine of an angle plus I times sine of the same angle. So cosine I sine, sometimes that's just abbreviated CIS because it's the same pattern over and over and over again. Right? If I had, for example, 1 plus I, that would be root 2 cosine pi over 4 plus I sine pi over 4. And sometimes that might be abbreviated as root 2 CIS pi over 4. The CIS is just this abbreviation for cosine of that angle plus I times sine of that angle. When we talk about complex numbers in polar form, the r is called the modulus, and people actually think of this as being the absolute value of a complex number. If we want to know how big a complex number is, we basically measure how far is it from 0. Right? That squares with how we do it on the number line. This distance r is measuring how big this is, how far away it is from 0. We can think of it as the size or absolute value. The fancy word is modulus, and the angle is called the argument. I don't know the source of that. Now, why do we care? Let's see what happens if I have two complex numbers. Here's z in complex form with an r1 and a theta 1. And here's w in complex form with an r2 and theta 2. I'm going to multiply them together. So z times w would be r1 cosine theta 1 plus I sine theta 1 times r2 cosine theta 2 plus I sine theta 2. So here's what I'm going to do. I'm going to pull out those two moduluses, or moduli. And then I have a binomial here and a binomial here. I'm going to FOIL them out. So I have cosine theta 1 times cosine of theta 2. My outers would be I times cosine theta 1 sine theta 2. I may need to give myself a little more room here. My inners would be I times sine theta 1 cosine theta 2. And for my lasts, I will have I times I, so that's negative 1, sine theta 1 times sine theta 2. So now let's group these based upon what's real. So my first and last terms don't have I in them. Grouping based upon what's real and what's imaginary. My two middle terms are imaginary. Cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2. Let me make this clearer. Just to be clear, you do not need to worry about all of these little details. Oops. I am showing you this. Don't worry about following every little thing. Just think about, what am I doing, right? Patrick is multiplying these together and he's just doing FOILing. It's really messy because everything's so abstract, but you've been FOILing since 7th grade or so. So here we have cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. Now here is where you may or may not recognize things based upon what you learned in trig or pre-calculus and how much of it you remember. But here's what I will tell you. This formula here, right? You can look it up if you've never seen this before. This is cosine of theta 1 plus theta 2. Right? We have these formulas where if we add angles or subtract angles or multiply angles, we can predict what the cosine of the new or sine of the new angle will be based upon old stuff. So if I want to know cosine of two angles added together, this is the formula. And this here is the sine of those two angles multiplied together. So what I have here is R1, R2, cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So I took my two complex numbers in polar form. I multiplied them together to get my answer in polar form. And let's look at how nice this pattern is. Here is our new R. Well, how did we find our new R? Just by multiplying together the R's we started with. What's R for the first number? What's R for the second number? We multiply them together, and that gives us R for their product. What about our new theta? Our new theta is what we get if we add these together. So it's very predictable. If I have two complex numbers in polar form and I multiply them together, I know the polar form of their product instantly. R times R gives me the new R. Theta plus theta gives me the new theta. This is so much more convenient than foiling. So let's just look at our rule. Here is our rule. If we multiply two complex numbers in polar form, then we multiply the moduli and we add the arguments. Now, I'm not going to go through the details, but by the principle of backwardsness, let's just trust your intuition. What if we divide? Dividing is multiplication only backwards. So we're going to divide the moduli, and we're going to subtract the arguments. What if we want to take a complex number and raise it to a whole number power? Right? What if we want to raise it to the third or fourth or fifth power? Well, that's just multiplying over and over and over again. R times R times R times R, theta plus theta plus theta plus theta. So if we raise something to the nth power, what we're doing is we're raising the modulus to that power, and we're multiplying the argument to that power. So let's just look at a quick example here. Right. What if I wanted to know 1 plus I raised to the 6th power? Right, I'll show you how this is really slick. If we think of this in polar form, R is root 2 and theta is pi over 4. So what we have here is root 2 CIS pi over 4. This result, which is sometimes referred to as de Moivre's theorem, says if I want to raise this to the 6th power and I have it in polar form, I'm just going to take this modulus and raise it to the 6th power, and I'm going to take this argument and multiply it by 6. So root 2 to the 6th power is 2 to the 3rd, which is 8. CIS 3 pi over 2. And if we visualize that, 3 pi over 2 is the direction that points straight down. So we would be 8 units straight down. This is equal to negative 8i. We're going down 8 units in the imaginary direction. Contrast that with, oh, what if I foiled this over and over and over again and kept grouping like terms and kept remembering I squared is negative 1? You could do it, but this is so much more efficient. If you have something you can easily put in polar form, then multiplication, division, and exponents, right, whole number exponents, so much easier if you think of complex numbers in polar form. Right, so now things are going to get really interesting, right? And we're going to just think about, other powers or, other ways of doing exponents, right? So adding, subtracting, multiplying, dividing whole number powers, we understand how that works with complex numbers. Now, what if we want to do other things like square roots or trig or logarithms? there's actually a way of making sense of all of this. And the way in is to think about other kinds of exponentiation, right? And let's think about e. So something you've probably seen is that this is the limit definition of e, right? If you want to know where did e come from, one of the answers to that question is you do this computation where n gets bigger and bigger and bigger, you run a limit, it comes out to some number about 2.718, and by definition, we call that limit the number e. Now, I'm not going to go through the details, but by making a substitution, we can also show that e to the x is the same thing where we just put an x there instead of 1. Right? So basically, here is e to the first power, and here is e to the x power. Very similar process. So now, what if we think of this as, a function f of x, and we want to apply it to complex numbers? Right? What if I wanted to know what is e to the I power? Now, if we actually need to think about this based upon the traditional definition of exponents in terms of, it's e times e times e a certain number of times, that doesn't really make sense with an imaginary power, right? Frankly, that doesn't even make sense with, negative powers and fractional powers and irrational powers, right? We've kind of found ways around this, and we'll continue to find ways around this with imaginary numbers. So what we'll do is we'll say, all right, well, I know that this formula here is true for any real number x. So let's just assume it's also true for any complex number. Right? What does it mean to raise e to a power? Let's call this actually the definition. Right? So by definition, we'll say e to the I power actually means do this computation and run a limit. And what's so great about this, if we look at this computation, right, what are we doing? Addition, division, exponent that is a whole number. Right? Here we can assume that n is an integer. Maybe that was left out of the first part, but we can imagine just what happens if n is 2, then 3, then 4, then 5. Just what is the pattern if n is an integer? This will be our definition. And all of this computation is stuff we know how to do with complex numbers. We understand what it means to add complex numbers. We understand what it means to divide complex numbers. We understand what it means to raise complex numbers to a whole number power. So what's so great here is that all of this makes sense. We don't have to abstractly, scratch our chins and think, what does it mean to take an imaginary power of something? Right? We can just say, well, this is how e to the x works. We do this computation, we run a limit. That always works with real numbers, so we'll just assume it works with complex numbers as well. This is something that is done in math sometimes. That we have something that seems like it doesn't make sense, we figure out a way of making sense of it, and then we extend it in some way. So now, let's actually try to do this. So what if I want to raise something to an imaginary power, and instead of being very specific about raising it to the power of I, right, let's just imagine that it's I times something. And I'm going to call it theta for a reason that will make sense later on. So here we go. E to the I theta, by definition, right, what does it mean to raise something e to a power? It means we just put that in this expression and we run a limit as n goes to infinity, and we're allowed to assume that n is just counting up the whole numbers. Here's what we're going to do. We're going to look at this thing here. And we'll think about this in terms of polar form. That's partially why I'm calling this theta, because we kind of want to think of this in terms of angles. And this is another one of these things where if you're watching the video, follow along as best as you can as I do this. You are not accountable for all of the details, but I do want you to realize that everything I'm about to show you touches on something you already know from either pre-calculus or calculus. So here's what we're going to do. We're going to think about this complex number, z equals 1 plus, and I'm going to write it like this, theta over ni. So here is 1. That is its real part. And let's just say that's theta over n. So there is z. And I'm going to put z in polar form. So to find r, we know that's basically like Pythagorean theorem. So the square root of 1 squared plus theta over n squared. And to find theta, well, that's going to be, assuming we're in the first quadrant, which is a reasonable assumption right now, inverse tangent of theta over n. Theta over n is measuring this distance, 1 is measuring that distance. So z is this value of r times cosine of inverse tangent of theta over n plus I times sine of that same angle. Right, this is not pretty, but hopefully you're just following what I'm doing. I drew a diagram, I thought about what is r, I thought about what is theta, I'm putting this in polar form. And what we just learned here is z to the n power would be, let me write that better, this radical to the nth power, and then our new angle would be n times inverse tangent of theta over n, right? And I write it twice. And remember, we're going to run a limit of this. So we want to know what is the limit as n goes to infinity of z to the n. So let's actually think of this as two different questions. This is measuring r for z to the n. So question number 1 we want to answer is, what is the limit as n goes to infinity of this expression here that's measuring the modulus? We want to know something about z to the n, so we're separating it. What will be the r, the modulus for z to the n? That's our first question. And then what will be the argument? Again, as we're running a limit as n approaches infinity. All right, so I need to add some pages to do this. And I'm going to be doing some slick things. L'Hopital's rule is going to show up. Don't feel like you have to memorize all the details, but just appreciate that everything I'm doing is something you know. So let's do number 1 first. So here's what I'm going to do. I am going to say, all right, so we're trying to find the limit as n goes to infinity of this expression here. And I'm just going to go ahead and write that as 1 plus theta squared over n squared. That's a way of just rewriting what's inside to the n over 2. Right? I have the half power from the square root. Let's call that L. So we're going to do a little trick here. We notice that we have an exponential expression and the variable for this limit, right? Theta is a parameter that it just is what it is. But we're running this limit with n here, and it shows up both in the base and the exponent. So a trick that is sometimes used when you have the same variable in the base and the exponent and it's confusing to think about is to introduce a logarithm to separate them. So we're trying to find L. But here's what I'll think about instead. I will think about the natural log of L. So the natural log of L, by definition, would be the natural log of this thing here. All right, I'm just calling that L and I'm taking its natural log. Now I'm going to do a couple of little tricks. One is whenever we're dealing with a continuous function like natural log, it's continuous on its domain, and a limit process. Continuous functions and limit processes play nice with each other, so we can switch the order. This is one of these limit rules that sometimes you just do intuitively without even knowing it. So that's the first thing we're going to do. The natural log of a limit is the same as the limit of the natural log. And then I can use a log rule here to say, oh, the natural log of something to a power. Well, I'm going to pull that power in front as a multiplier. That's a rule you learned about how to manipulate logarithms. An exponent inside a logarithmic expression can become a multiplier in front. So now I am just going to do little tricks here. This is an indeterminate form. This part is getting infinitely big. This part is getting closer and closer to 0 because this is getting close to 0 and it's like we're taking natural log of 1. So we have something that's getting bigger and bigger and bigger and bigger times something that's getting tinier and tinier and tinier and tinier. By intuition alone, we don't know what's going to win. But with indeterminate forms, we can do L'Hopital's rule. And the trick for L'Hopital's rule is let's turn this into a fraction by saying, no, I'm not multiplying by n over 2, I'm dividing by 2 over n. So now I'm going to do L'Hopital's rule. Okay, this will be a little bit messy, but nice things will happen. Actually, let's just do this on the next line. So our derivative of the top there, so natural log of something, here's what we've got. And then by the chain rule, we multiply by the derivative of this. So we basically have theta squared. We basically have theta squared. This is just on the side here. Times n to the negative 2. That's what that is. So the derivative, right, from the point of view of the limit, theta squared is just a number. And then the derivative of n to the negative 2, where n is the variable, would be negative 2 n to the negative 3. And then over here, 2 is the coefficient. We have n to the negative 1. Derivative there is negative 1 times n to the negative 2. All right, so now let's just try to simplify this. I will notice that I have a negative 2 here and a negative 2 here that cancel. This is n to the negative 2 in the bottom, which is really like n squared in the top. This would be n cubed in the bottom. So after we cancel those, we have 1 n left in the bottom. This is left, and this is left. Let me write this cleaner. N is growing to infinity. So this part is approaching 0, which means this denominator is approaching 1. So this whole thing is approaching 1. This is just equal to theta squared, whatever that was. So our numerator is theta squared, some specific number. But our denominator here is growing infinitely big. So regardless of what theta squared is, we're dividing it by bigger and bigger and bigger and bigger numbers. So that limit is 0. So now let's remind ourselves what we were actually calculating here is natural log of L. So let's just summarize. Natural log of L is equal to 0, which means L is equal to e to the 0, which is 1. And let's just recall, this is basically the R we were trying to find. for this process of raising a complex number to the nth power and running the limit, that limit is 1. Okay, so let's just go back and understand what we were doing. We're trying to make sense of the limit of this whole thing. We found the limit of this part. Now we're going to find the limit of this part. So this is number 2. That power of n is, yeah, that's just an error from before. That shouldn't be there. Sorry about that. Right, it's just, oops. We're just multiplying the original angle by n. So this should not be here. Sorry about that. As before, we have an indeterminate form. This is growing, oops. This right here is growing bigger and bigger and bigger because n is approaching infinity. Theta over n is growing really tiny, close to 0. Inverse tangent of 0 is 0. So this is growing bigger and bigger and bigger. This is growing tinier and tinier and tinier. It's not clear who wins, and I accidentally put that back. All right, so let's use L'Hopital's rule again. Let's turn this indeterminate form with multiplication into an indeterminate form with division, because that lets us use L'Hopital's rule. All right. Derivative of inverse tangent is 1 over 1 plus x squared. In this case, it is theta over n squared. And then by chain rule, we multiply by the derivative of this. So I have theta, and then n to the negative 1. Its derivative is negative 1 times n to the negative 2. And that's exactly what we have as the derivative in the bottom. So we notice that these are the same. So this limit is 1 over 1 plus theta over n squared times theta. Theta is some specific number, n is the one that is changing. So this is getting closer and closer to 0. We're squaring it, so this whole thing's getting closer and closer to 0. So our denominator here is approaching 1. Our numerator is equal to 1. This is equal to theta. So when we run all of this, this limit is theta, whatever theta was to begin with. So let's really summarize all of this that we found here. Oh, I have the page already. So let's just recap what we're doing. We want to figure out, in a very general way, what do we get when we raise e to an imaginary power? By our extended definition of what it means to raise e to a power, we're going to do this. So we put this in polar form. We've done all of this work. And so e to the I theta, where we are right now, we know that e to the I theta is the limit as n approaches infinity of this crazy expression we have down here. Oops. In limit number 1, we learned that this r in front, as n goes to infinity, approaches 1. In limit number 2, we learned that this argument approaches theta. So the limit of this whole thing, what we're finding is that e to the I theta is 1 times cosine of theta. Don't even need those parentheses. Plus I times sine of theta. Don't even need that 1. So when we raise e to an imaginary power, what we get is a complex number that, if written in polar form, is super simple and easy to understand. Once people learn this, sometimes they stop writing the CIS and they just use this as their abbreviation for cosine theta plus I sine theta. But many students don't know where this comes from, and that feels artificial. Okay, but what does it mean to raise e to this imaginary power? It means the real part is cosine of whatever we were multiplying I by, and the imaginary part is sine of that. So here is our results. This is just tremendously elegant. If we open ourselves up to this notion of complex numbers and writing them in polar form and extending things like the exponential function so that it can apply to complex numbers, then we get this very elegant result. And once we know how the exponential function is related, we can use that as our toehold to think about other functions like square roots of complex numbers, the logarithms of complex numbers, trigonometric functions of complex numbers. I won't get into it, but once we have this, we can start to unpack everything else. If you want to raise an e to an imaginary power in polar form, this is what you get. So now, I've cheated a little bit. Now, what if theta is equal to pi? We have e to the I pi is equal to cosine of pi plus I times sine of pi. Cosine of pi is the number -1. Sine of pi is 0, so this part is just 0. And this is sometimes rewritten as e to the I pi plus 1 equals 0. Just moving this -1 to the other side. Maybe you have seen this formula before. Right? It's one of the many things in math called Euler's formula. And a lot of people, what they like about this is it takes 5 of the most important numbers in math. You could argue the 5 most important numbers in math, right? 0, right? 0 is our additive identity. It represents nothing from the point of view of addition. Obviously, 0 is a very important number. 1, obviously, is a very important number. It's our multiplicative identity. From the point of view of multiplication, this is nothing. E, we know, shows up in all kinds of mathematical formulas. Pi shows up in all kinds of mathematical formulas. And I is our imaginary unit. It is the single imaginary thing we have to think about in order to unlock all of the complex numbers. This formula takes those 5 numbers and no other numbers and explains how they're all related to each other. E shows up exactly once. I shows up exactly once. Pi shows up exactly once. 1 shows up exactly once. 0 shows up exactly once. There are no other numbers, and this is how they're related. There is something very elegant about this. Right? There's so much built into what this means in terms of all of these definitions with polar forms, with limits, with stuff like that. But once we can get past that, the result is astoundingly simple. All right, this has been a very long video. I hope some people appreciated what's here. Obviously, you don't need to know all the details, but we will leave it at this.